Alright guys, in this section we're going to be discussing sum and difference formulas, and these formulas will be the first of several trigonometric identities and formulas we will derive and use moving forward. Alright, so here we have the identities. We have sine of a sum, sine of a difference, cosine sum, cosine of a difference, and also tangent of a sum, tangent of a difference. One of the applications that we'll be able to do with these formulas is to find exact values of trigonometric functions involving sums and differences of special angles. For instance, here in this first example, we have find the exact value of sine of 75 degrees. Our first thought would be to think of the unit circle, but if you remember unit circle, 75 degrees is not a special angle from there, so we're not going to be able to find sine of 75 using the unit circle. So here is where the formulas come in handy. If we can come up with a combination of two angles that add up to 75 degrees, or whose difference is 75 degrees, then we can use this formula. Now those two angles have to be in the unit circle so that we can find the exact answers. And luckily we can write 75 degrees as 30 plus 45 degrees, and 30 and 45 both are in the unit circle, so then we'll be able to use the formula and compute the exact value. So sine of 30 plus 45 degrees, using the formula above, we get sine of the first one 30 times cosine of the second one plus sine of the first one times cosine of the second one. All those values, trig functions of those special angles, are known from the unit circle, so you can just plug those in. They both happen to be on this first quadrant, so everything is positive, and there we have it. The rest is just calculation, and again, if our objective here is to have an exact answer, then do not put this in the calculator, just simplify it and write the exact values. So from the first part, we have the square root of 2 over 4 plus square root of 6 over 4. They're both over 4, so I can put all of it together in one fraction. Square root of 6 plus square root of 2 all over that 4. And there we have it. Okay, here's another example. One where the angle is in radians. Remember, when I started with one with degrees, so that you kind of get comfortable with the formulas, but pi 12 is not in the unit circle, so you want to come up with two angles that added together gives you pi 12, or if you subtract them gives you phi 12, or take the difference of the two is phi 12. And here we find one that is pi thirds minus pi fourth is pi 12s, so that would work because pi thirds and pi fourths are both in the unit circle, and then we can use our formula from above. Now, guys, one thing to note here is that this combination is not unique. So if you look at the first example that we did, 75 is 30 plus 45, but you could also find another combination that works. And it doesn't have to be a sum, it could be a difference as well, as long as the two angles are in the unit circle. So for instance, 120 minus 45 would have worked on the first example, and 120 is in the unit circle 45 as well. So don't think that this combination is unique, but it may require you to use a different formula, but the answer should be the same at the end. Okay, so here for cosine, just very convenient, pi 12 is equal to pi thirds minus pi fourth, and then we can use your formula and just plug in the values here. And notice how we get not just something similar to the previous example, but it's actually the same answer, right? And is that a coincidence? Well, think about sine of 75 degrees is equal to cosine of pi 12s. If we were to change that pi 12 to degrees, you would see that pi 12 is 15 degrees, and this is not a coincidence. This is, we already knew that sine and cosine are cofunctions. And remember what we've said before, it's actually an identity, cofunction identity is the sine of an angle is equal to the cosine of its complement. Okay, here we have another example where we're given some information about the two angles, U and V, and we're asked to find, in this case, cosine of the sum. So we're going to start by using our identity here, cosine of U plus V is equal to cosine of U times cosine of V minus sine of u times sine of v. Make sure you are using the right identity. So for cosine, whenever it's addition, sum is minus on the identity. So it's different than the sine of a sum or a difference. So we're going to take the information that we have, and notice how they give you the sine of u and they give you cosine of v. And we're going to use our right triangle trigonometry to figure out the other trig functions that we need. Notice how we don't have cosine of u, but we have cosine of v, and that's negative 3/5. Okay, minus we have sine of u, it's 12 over 13, and we do not have sine of v. So here is where our right triangle trigonometry comes in handy. We can set up two triangles here, one containing u and the other one containing v. So if we look at sine of u being 12 over 13, I can set that up and figure out my third side, and that's a quick Pythagorean theorem operation calculation. And same thing for v, a different triangle here. Cosine of v is negative 3 over 5. We can forget about the negative for right now. Cosine is adjacent over hypotenuse, and with a quick Pythagorean theorem I can figure out the third side, and we have 4. Now with that, we should be able to figure out the remaining trig functions that we need. And notice how this u and v, u is in the first quadrant according to the problem, and v is on the second quadrant. So that's going to be important when we come up with the ratios, because some of these values will be negative depending on what quadrant we're in. So notice cosine of u is adjacent over hypotenuse, that's 5 over 13. And since u is in the first quadrant, everything is positive on the first quadrant, so we don't have to worry about that, adding a negative there. For the sine of v, okay, we have 12 over 13, and sine of v is 4 opposite, right, over hypotenuse, 4 over 5. And since v is in the second quadrant and sine is positive in the second quadrant, it's just 4/5. After we plug everything in, the rest is just to simplify this expression. We have negative 15 over 65 minus 48 over 65, and they're both under 65, so we just combine the numerators into a negative 63 over 65, and then we're done. There's nothing else to simplify, and we still managed to get the exact answer. Okay, here's another example where we're asked to find an algebraic expression, and what we're going to do is start with that identity here, and this is a sine of a sum. So the identity says, right, r tangent of 1 is our u here, and r cosine of x is our v. So sine of the first one, the u, times cosine of the second one, and since we're adding, it's also going to be plus sine of the second one, which is r cosine of x, times cosine of the first one, which is r tangent of 1. Right, all I've done here is apply my identity, sine of a sum, and then we're going to use my trig to simplify, right? R tangent of 1 is from the unit circle is just pi-4, and we're going to have sine of pi-4 times cosine and r cosine cancel each other out because they're inverses of each other, so we just have x there. Plus, for sine of r cosine of x, we're going to need that skill that we learned on previous chapter to express that as an algebraic expression. All right, so I'm going to do it here on the side, and if you recall, we label this r cosine of x, or the argument of sine, as some theta here, and by definition cosine of theta has to be equal to x, which we can write as x over 1. Using our right triangle trigonometry, we put theta in our somewhere here in the triangle. Using cosine adjacent over hypotenuse, we can use Pythagorean theorem to figure out that third side. So we ultimately want to find sine of theta. So sine of theta would be opposite over hypotenuse, which is just square root of 1 minus x squared. All right, well, that's what goes here in our identity. So sine of r cosine of x that whole thing is equal to the square root of 1 minus x squared. Now times, we're going to have cosine of, again, pi fourths. Our tangent of 1 is pi fourths. Moving on, we have the sine of pi fourths from the unit circle. That's just square root of 2 over 2 times x plus square root of 1 minus x squared times cosine of pi fourth, which is also square root of 2 over 2. All right, the rest is just simplifying this a little bit. Everything is over 2, so I can just put all of it together under one fraction. Okay, so I combine a couple of things there, but there's nothing more that I can do here. So I'll just put all the numerator together and divide it by 2. All right, here's another example where we're asked to verify. Remember, we've done verification of identities before. And now that we have new identities, we can use them to verify this cofunction identity. Now we already know or seen this cofunction identity before, and we know this one to be true. Okay, so we're going to use our identity for the sine of a sum, and you just split it up here. Okay, notice how that sine, cosine of pi halves is 0, that goes away with the sine x, and we end up with the negative cosine x, which verifies what we have on the right side. Okay, here we have a couple more examples where we're asked to express or write these expressions as trigonometric functions of data. We're going to use our identities here. And we have a difference, sine of a difference. We have also tangent of a difference. So all we have to do is apply the right identity. Once we set it up, we're going to be able to evaluate some things, and the rest is going to be in terms of theta. Sine of 3 pi over 2 is negative 1 from the unit circle times cosine of theta minus sine of theta times cosine of 3 pi over 2 is 0. That eliminates the whole term there, and then we end up with just negative cosine of theta. For the other one, we have tangent of the first one, theta, minus tangent of the second one, pi over 4. All of that divided by 1 plus tangent of theta times tangent of pi fourths. Now, tangent of theta is right the same. Tangent of pi fourth, we know that to be equal to 1 from the unit circle. We divide all that by 1 plus tangent of theta times 1, which because tangent of pi fourth is 1. And then rearranging the terms a little bit, we get tangent of theta minus 1 on the numerator over tangent of theta plus 1 in the denominator. Another example where we're asked to find the solutions of this equation here on the interval 0 to 2 pi. So notice how we have sine of a sum plus another sine of another sum, all of that equal to 1. So we're going to go ahead and just apply our identities here, our sum identities, or formulas. And so we set it up in the following way. All right, so notice how in the first one we have sine of x times cosine of pi halves plus sine of pi halves times cosine of x, plus the second one would be sine of x times cosine of 3 pi halves minus sine of 3 pi halves times cosine of x. All of that equal to 1. All I've done is I've applied the sine of a sum formula and sine of a difference formula. Once I've done that, I'm going to be able to evaluate some of these trig functions, and the rest we'll leave it in terms of x. We have sine of x times 0, because cosine of pi halves is 0, plus sine of pi halves is 1, that is times cosine of x, plus sine of x times cosine of 3 pi halves from the unit circle, that is 0. So then sine of x times 0 minus negative 1, sine of 3 pi halves is negative 1 times cosine of x, all of that equal to 1. A couple things are going to cancel out. Anything times 0 is 0, so all those things go away, and we end up with cosine of x minus negative, so that makes it positive, plus cosine of x equal to 1. Adding those two together, we have 2 cosine of x equal to 1. Divide everything by 2, get cosine of x equal to 1/2. And we're done with the algebra. We can use our trigonometry now to figure out when is cosine equal to 1/2. And since we only want the solutions from 0 to 2 pi, cosine is equal to 1/2 at pi over 3 and 5 pi over 3, first and fourth quadrant.